It's actually kind of cool. One second. So my proctor left, so I don't know if I'm supposed to start now, but I guess I'm going to start. So this is kind of annoying. Oh, there it goes. Okay, my name is Robert Graham. My Twitter handle is erratarob. My blog is at blog.erratasec.com. This URL is the URL of this presentation up on Google Docs. So you can type in this URL and you can download the presentation on your computer as I'm presenting it. If you can't type in that URL, I just put it in my timeline as well, so you can look at my Twitter feed as well. So I have a crappy title for my talk. So here's what it's about. There's two parts to the talk. The first part is an idea that sort of the justification for the second part of the talk, which is about my tools and code based on that idea. So the first talk is more general and high level, and then the second part I'm going to delve into code. This is the idea that I'm getting at. Who's familiar with this picture? So pretty much everyone. This is the Tacoma Narrows Bridge. It was built in 1940. It was the third largest span at the time, behind the Golden Gate and the Washington Bridge in New York. And during construction and soon after construction, it behaved like this during high winds. And 5 months after it was completed, it fell into the river. And the thing about this bridge is that it changed how bridges were designed. It changed how the textbooks were written. From that moment on, in 1940, every large span bridge built, every engineer knew about the Tacoma Narrows. No matter where you were in the world, if you built a bridge, you knew about this thing. And it's become such a big thing in engineering that we as non-bridge engineers, we know about this story as well. So this is a picture, not a photograph as you can tell, of the Titanic. It had the same sort of effect. When it sank, it changed how the codes were written, how the textbooks were written, how international agreements were written. The change in how what we did in the Atlantic changed. So that all these new international accords were produced that are still in effect today. It went back to the drawing board, redid things, and now we no longer crash into icebergs. So the same thing happened on September 11th. The Twin Towers fell, and engineers went and investigated why they fell. And the reason they fell is because when the planes hit the buildings, they hit the girders. And the girders were covered with insulation so they wouldn't melt during under a big fire. Unfortunately, when the planes hit, they stripped the insulation from the girders, so then they were exposed to the fire. Moreover, the fire couldn't be put out because it was full of jet fuel. So the sprinkler system was inadequate. Furthermore, since the designers expected that any fire in these buildings would be contained to just a few floors, the emergency stairwells in the middle were not adequate to evacuate the entire building. So again, they went back to the drawing boards. They said, okay, now planes are now a threat that we have to consider for high-rise towers, along with hurricanes and other things. We have to improve the fireproofing on the girder so that they're less likely to be stripped away when a plane hits, and we need better escape routes. The lesson I'm trying to drive here isn't that we need to take security more seriously or safety more seriously. The issue here is when bad things happen, we've gone back and rewritten the textbooks. If you are a bridge engineer, you know about Tacoma Narrows. If you're a boat engineer, you know about the Titanic. If you're a architect, you know about why September 11th, why those towers fell. And just because you know doesn't mean you're going to take the safety seriously. There's only so much fireproofing you can put on a girder. There's only so much buttressing you can put on a span on a bridge. There's only so thick that the boat's hull can be. So you're not allowed to necessarily take safety to the extreme from these lessons. What you're taught is what happens, so that when you make your decisions and trade-offs of how you're going to build these things, you already know how they're going to fail. So how many people know in the last 10 years that the biggest vulnerability has been on the internet? Well, it's SQL injection. And so this is a common textbook, at least in the United States, that when people, if you go to college this year and take a class in database programming for websites, how to build a website, this is likely going to be the textbook that you use. So I went onto Amazon.com for the little Kindle reader, downloaded and purchased this textbook, and then did a search for injection. And I found one result. And it was about the picture on the cover, which is a platypus. And this was the second edition. It was published in 2009. Basically, 9 years after SQL injection had been the top vulnerability on the internet. So what we see here is that new engineers are not being taught about the failure, about why websites fail. We're not going back to the drawing board. We're not revisiting the decisions we've made previously. So another one of the most common problems on the internet is buffer overflows. And this is the college textbooks that people read today. And it was published in 1989. And really hasn't, this is the second edition when they standardized in 1989. And there really hasn't been an update since. If you learn C programming in college today, you do not learn what a buffer overflow is. If you're a programmer, it's sort of this mystery thing you might have heard of, but you don't take it seriously as a real threat. So that's our problem that we have today, is we have not gone back to the beginning and rewritten the textbooks, and people today are making the same mistakes over and over and over again. They're not like a bridge engineer, they're not a boat engineer, they're not an architect. They haven't learned the lessons of history. We're teaching students. So when you hire someone for your company today, you hire a C programmer who doesn't know buffer overflows. If you hire a web app designer, they've never heard of SQL injection, or if they have, they don't take it as a serious threat. So here's an example of how this comes out in the marketplace. There's a bunch of professionals who set up their own little blogs. And if you want your own blog, here's what you do. You go to, I don't know, some hosting site. They've got a little VPS system, virtual hosting. They got Apache, Mod, PHP, WordPress managed by cPanel, and all sorts of other applications for you. And it's wonderful. And they charge you $3.95 a month, and it's a great price. And it seems to work. Just a few clicks of the button, you create a website, and it all works. I did that last week. In 20 minutes, from the idea I had of a website to actually putting it up on the internet was 20 minutes. And it seems to work. And over time, this professional, he or she is well known in the industry, and more visitors from their profession come to their blog, and they start getting complaints that your blog is down. And they don't know why. They call support doesn't know why, bunch of activity, and everyone's clueless. So they just solve the problem by looking for another hosting site, but it has the same architecture. It's the same VPS, virtual hosting, the same Apache, the same Mod PHP, the same WordPress. So they give up and then go with Cloudflare, who put something in front of their website, essentially, to mitigate the problem. And here's what the problem is It's spiders, indexers like Google itself, or other indexers looking for other stuff, like trying to scrape email addresses off of websites for spam. Or it's these scrapers who are trying to steal your content and image, either because they're trying to reuse it and just get in search engines and then get traffic driven to their site for advertising, or they're the SEO bots that take your content, mix it around, combine it with other content, so it looks real, but it's not, but it's designed to create virtual websites that they can use with Google to have all these incoming links to whatever site they're trying to promote. So these things, when they come and hit your website, they're very, very active, and that's why your website is down. You have WordPress, who has all these 1,000 posts you've done over the last 5 years, but they're not in the cache. And so they hit the site, and WordPress starts working hard to regenerate all those pages, and while it's doing that, your site's down. Oh, and then the comment spam things, so the tools that try to come onto your site, put comments on there, like I really like your article and make money at home and drive more content, more links to their site. So this is a graph of what the underlying problem is with Apache, is it doesn't scale. And by scale, we mean that as we get more and more connections to the server, it hits a wall where it just sort of just falls over. And the issue here is that scaling is a different issue than performance. So we're performing at 100% of the server's capacity. And then we hit this wall at, let's say, 4,000 connections. And then it falls over. So we say, okay, I want to go to 8,000 connections, so I'm going to buy twice a fast server. I'm going to double the speed of the server. So it goes to 200%. That's the red line. But when you look to the right, though, we've only gone from 4,000 to about 6,000 connections. We haven't doubled the number of connections that the server can handle. And then quadrupling it, that's the green line. It's kind of quadruples off the top of the screen. But to the right, we still haven't doubled our how many connections the server can handle. And if we keep going from the green line to 8 times to 16 times, no matter how much we're adding this, we're not really doubling the amount of performance. We're at 5,000 connections there, I guess, and going all the way to the right, we still haven't reached 10,000 connections. And that's the fallacy that we have. We have this idea that Moore's law will cure all ills. That, oh, I'll just wait till next year when I get twice the processor in the server, and it'll have twice the performance. But performance and scalability are these different issues. I can double, quadruple, whatever up the top of the screen there, but I'm still not handling more connections. When SEO bot comes to the server and scrapes it and generates 10,000 concurrent connections, my server goes down. And no matter how much more I've spent on the server, it still goes down. So the solutions we're looking for are to go back to the textbooks. It's like rebuilding the bridge at the Tacoma Narrows. Why did it fail? Why did my website go down? Let's go back to the drawing board and figure that out. And the solution that we've come up with is asynchronous event-driven design. So instead of creating one thread per connection, we have one thread per core that's on the CPU, and then we handle all the connections with that small set of thread. And the result is the same amount of performance regardless of the number of connections. And that's the orange line here. You have an asynchronous server. It may not be as fast. Over on the left-hand side was only a few connections to the server, but it doesn't slow down as you get more connections. And that's what the server called Nginx. To the right there, the green line, Nginx. That's what that server is based upon, is an event-driven design. And you can see here, Apache is falling down. Apache is the blue line. Apache dominates all the servers on the internet. Everything's written in Apache almost, even the high-performance servers. And these are even busy servers. This is market share of the top 1 million busiest sites. And we see they're getting more and more unhappy with the fact that Apache doesn't really work, that they need to put things like Cloudflare in front of it. And then Nginx is the new thing. But unfortunately, they're not teaching Nginx in college. They're still teaching Apache. And the thing to remember is that the hackers know about this. The scrapers and the indexers and the bots, they're written with the same event-driven design as Apache is. And that's why they take down Apache, the same event-driven architecture as Nginx. And if they hit Nginx handles it just fine, but when they hit Apache, Apache falls over. And so what we have, and the reason we have this is that back in the late 1990s, when we were first building the whole .com era, we were doing prototypes. That we could get anything to work at all was the problem we were trying to solve. We were building prototypes back then. Prototype servers, prototype companies. Maybe my company won't work, my pets.com won't work. But the problem we have today is we know how to make a website. Teenagers, 12-year-old kid can put together his own website. We know how to do that. We don't have to struggle with that problem anymore. Our problem today, though, is getting those servers in production, in operation, so that when we plug it into the public internet, that doesn't fall over 10 minutes later because an SEO bot comes along and hits it. Or that hacker comes along with SQL injection or all the other ills. So that's our problem, is we need to go back to the textbook and say, hey, it's not Apache PHP, it's things like Nginx and FastCGI. And so I was talking about this with someone yesterday, or 2 days ago, and he was quite offended that I would say this, but Apache and Mod PHP do not work in production. They are not inherently designed to be exposed to the public internet of the Internet of 2013. They were designed for the Internet of 1999. And the solutions we have for this are bad solutions. So this comes to the title of my talk, is why I call it data plane. This was a concept first done back in the telecom era, starting back in the 1950s when you had manual operators who would have to take a wire from one location and plug it into another location in order to complete a phone call. And the operators were the control. The wires themselves were the data. And then in the 1970s, we had digital switches for the telephone system. And that was the first Unix computer, was built for a telephone switch, to be the control of the switch. The Unix computer didn't actually carry the voice traffic itself, it just controlled the voice traffic. The voice traffic went over hardware, the data plane. So that's how telecommunications engineers address the problem. We have control over here, which is slower, doesn't have to be fast, it has to be functional. And then the hardware is where we go really high speed. And that's where we are today. Apache, Mod PHP, databases, business logic, those are all great in the back end. But we need things like Nginx, Light HTTP, Varnish, hardware devices on the front end that are exposed to the public internet. Okay, now let's talk about DNS. DNS has the same sort of issue. DNS is a critical infrastructure to the internet. It's not really a service like the DNS server. So I've been working on 2 projects for the last year. One of which is a DNS server that I'm going to describe in the following slides, where I'm going to get into a little bit of code about going back to the textbook and redoing what textbooks should now teach. I also, related to that, I've built a little port scanner. And so you can go online to GitHub and look at the source code of both of these projects. So let's talk about DNS. So back in 2000, this is a graphic I got from some site. I forget which one. It has a great infographic about the growth in the last 10 years. It was mostly focused on Facebook. But it shows the number of users. In 2002, we had 600 million users on the internet. And in 2012, we had 2.3 billion. So the internet's grown about 5 times in the last decade. Here's another graph. This is from Wikipedia, where it shows the number of reachable hosts on the internet. And this is a logarithmic graph. So 10 years ago, it was 100 million hosts or reachable IP addresses. Now it's 1 billion. Let's talk about smartphones for a moment. Smartphones now outsell dumb phones. So more of us around the world have iPhones and Androids than have the older non-internet browsable phones. In the last quarter, these numbers, by the way, are from Gartner from last month. Last quarter, 225 million smartphones were sold. That's 225 new smart devices attached to the internet. So for the next year, that'll be 1 billion devices. So there's 1 billion devices now on the internet. It's going to be 2 billion next year. And the growth is huge. 40% growth of smartphones since 2012. Here's an example of a smartphone, an HTC One. It was released a few months ago by HTC. It's their flagship phone. It has 802.11ac on it. That's the new Wi-Fi standard that goes to, I don't know, gigabits. Someone did a test of their phone on a high-speed home connection. And from the phone, they were able to get 83 megabits per second, which is enough to easily do 50,000 packets per second. Now let's talk about Bind. Bind is the most popular DNS server on the internet. They're redoing it. There's a new version called Bind 10. And here's one of their benchmarks. And what we see from the benchmark is kind of not clear. I can't really read it on myself being this close. But the numbers, what we see here is that Bind struggles at, this graph goes to 40,000 at the top there. It struggles at fairly low rates of speed. It's enough that one cell phone connected to Wi-Fi can take down a DNS server on the internet. And that's kind of unreasonable. So here's the popularity of Bind. This last week I scanned the internet and sent a version bind request to every IP address on the internet. That's my little scanner thing. So, and I did a report of the different versions. I parsed the addresses and stuff to narrow it down to what server they were. So Bind is more, DNS servers run Bind exposed to the internet than any other server. These other servers like Nominum, PowerDNS, NSD go a lot faster than Bind, but Bind is still the most popular. But as we see, someone with a cell phone can take down a Bind server. And this is my impression of Bind. It's a bridge that engineers repeatedly build the same way, hoping that next time they'll solve the problem without ever addressing the problem. So, the reason for this is not necessarily that Bind is bad, but it's like Apache. It's not designed to be exposed to the internet. It's really designed for the functionality of how do we do transactions with DNS names, how people update a database and that sort of thing. It's not designed to actually be the actual server that serves the internet. Okay, so let's talk about code. So today's operating systems are based on the idea that today's textbooks are based on the idea that it's the operating system that should do all the heavy lifting for you. So that when you produce an application, you produce a lightweight bit of code that leverages everything else that the Linux kernel or the Windows kernel or BSD kernel does for you. So you don't do TCP/IP, you just write to the sockets layer. You just call malloc, you don't know how memory happens and how malloc works. You create threads, and you use simple primitives like mutexes to synchronize them so that you don't corrupt data. Oh, and you create one thread per task rather than something else. So going back and rewriting those textbooks, let's think about a different way of creating stuff. Instead of going through the TCP/IP stack of the kernel, let's just go to the hardware ourselves. And I'll show you that in a moment. Instead of allowing the operating system to manage memory, let's manage memory ourselves. Rather than having one thread per task, let's do one thread per core and use the event-driven design. Instead of using mutexes for synchronization, let's use these lock-free primitives. More advanced primitives that don't have the problems that mutexes have. So here's the first step, doing our own TCP/IP. Here's a map of the Linux kernel. As you can tell, it's got a lot of complexity. When a packet arrives in Linux, this sort of convoluted path going up through all that stuff is that it takes. And Linux is actually fairly efficient in that it can handle 1 million packets per second without too much trouble. But what we want is something bigger than that, 10 million packets per second, 100 million packets per second. So we want something that will take a packet at the very bottom and ship it all the way to the top to our application, bypassing that whole mess. There are several things that will do this. What I do, Intel has some drivers, FreeBSD has some drivers. There's some proprietary vendor cards that have drivers that do this. What I use in my project is something called PF-Ring. It says DNS there, but it should have been DNA. And what DNA stands for is direct NIC access, NIC meaning the network card. And how it works is pretty simple. It replaces the existing driver with its own. And that driver disconnects the network hardware from the kernel. So the kernel thinks of it as some unknown device rather than a network device. And then it connects it directly up to a user mode application. You have a shared library that you use, and you call functions in the shared library to receive packet or transmit packet, and it goes directly to the hardware. And the theoretical speeds of this are enormous. For a fairly low-end machine, like a quad-core desktop, in theory, you can get 100 gigabits per second, or 100 million packets per second. It's just as obscene. And it's got a lot of tricks with it. Modern cards can split its stream, one network card, into multiple virtual network cards. And the attraction of that is that you then do one virtual adapter per thread. And the attraction for that is that each thread gets the network data itself without having to share it with other threads. So imagine a DNS server. Every packet that comes in, it receives, processes it, and generates a response. It doesn't have to synchronize with other threads to do that work. So the network, by splitting the streams at the network card layer, I don't need to have thread synchronization at the application layer.
Does that work for stateful protocols?
It does work for stateful protocols. It has something called, I forget what it's called. It hashes the TCP/IP socket for you on the hardware in the network card, so that when you get the second packet on your TCP connection, it goes to the same thread and core. And as you said, it's bitchin'. So I can get the packets, but I need to do something with them. Now, TCP is a fairly complex state table, as we all learned from reading the RFCs. But the raw packets are themselves fairly simple. Ethernet's 14 bytes. Source, destination, type, that's all there is. IP header is 20 bytes. Length, source address, destination address, checksum, there's not much there. UDP is even less. Source, destination port, checksum, and length. That's all there is. I don't need really anyone to do that for me. I can do that much myself with just raw code. And so here's the result. So here's my scanner running. It's not running connected to the internet as such, because it's my home connection. It's only 10 megabits up. But it's blasting out to the local 10 gigabit Ethernet switch at 25 million packets per second. And that's what you see with the little red line underneath there. And you see up in the upper right, I got the dash PF-Ring option, which means I'm using the PF-Ring driver. So I'm blasting out 25 million packets per second. Now, if you're thinking about this, you're thinking about, well, wait, 10 gigabit Ethernet, the maximum is 15 million packets per second. That's the maximum theoretical bandwidth. Well, what I'm actually doing is I'm using two cards. So this is a quad-core desktop. It's 3.1 gigahertz Ivy Bridge, Sandy Bridge processor. So there's nothing special about this except for the fact that it's a 10 gigabit card with a special driver, and my scanner just sits in a tight loop generating those packets from the previous slide and just spewing them out at 25 million packets per second. So it's not quite the 100 million packets per second limitation, theoretical limit, because my code has to go off and do stuff, but it's close. I mean, it's 25 million packets per second. It's far beyond what you can get through trying to send those packets down through the Linux stack. And Linux is, by the way, very, very good with this network stack. I don't know if you guys have been watching this sort of thing I do, but Linux 2.6, the limitation was about 500,000 packets per second with a low-end system, and now it's easily 2 million packets per second on a low-end system on Linux version 3.4. It's gotten a lot better, and it's really cool. It's a lot faster than, like, let's say, Windows. Okay, so that's my scanner does that. My DNS server is a bit slower. So my benchmarks are that I can get requests and spit out a response about 6 million packets per second per core. And the more cores I have, it scales so that 4 cores does 24 million packets per second. But that's run repeated queries. The problem with DNS, though, is that you have a database lookup for every packet that you receive. Someone requests a random name in your database, and you got a large database, it's not going to be in the cache. So the cache misses cause it to go basically half as fast. And so that's the primary performance limitation of my DNS server, is those cache misses. So that's where one of the other things I described earlier was now memory management. Let's take control of memory management from the operating system. Now, I have the .com zone domain. It's an 8 gigabyte file. It's got 200 million zones or domains in it. It requires about 16 gigabytes of RAM in order to load the entire file into RAM and then format it in my big database in memory. And I say database, it's really just a hash table. And remember, the operating system's got page tables, got virtual memory. So I use more memory than there's physical RAM, it'll page things out to disk and stuff. And it's got memory protection, so if I overwrite some other region of memory, it won't actually overwrite it. And that paging system also takes up memory. For 16 gigabytes of RAM of a large database, it's going to require 32 megabytes of page tables. Well, the CPU only has 8 megabytes of cache, which means the page tables themselves won't fit in the cache. So that means every time I have a DNS request that's random, it's 2 memory cache misses. And a cache miss is really expensive. It's 100 nanoseconds when I don't have it in the cache, and then I gotta go out into main memory. So the solution to this is take control of, as I said, memory management. So the default page size on Linux is 4 kilobytes. That's why then you do the math and yada, yada, yada. It's 32 megs of page tables. And random access memory is now 200 nanoseconds to resolve. But I can then choose something called huge pages instead. And huge pages are 2 megabytes in size. Do the math, that means I only need 64K of paging tables. 64K fits easily in the cache. And then my random access speed then goes down to 100 nanoseconds, and then my DNS server goes quite a bit faster. So this one change is about a 50% increase in the speed of the DNS server. Now let's talk about thread synchronization, because this is really the big win. Most applications, when you benchmark them on 1 core and 2 cores to 3 cores, they go faster. Then you go to 4 cores and 5 cores and 6 cores and 10 cores and 12 cores, and they go slower and slower and slower. And that's because they're using mutex's fairly inefficient thread synchronization. We all know that we have to do thread synchronization or the program crashes. But the way we're taught in the textbook is really the wrong way. It scales to only a few cores and then it dies. The new textbook is new techniques. The number one most important technique is to avoid data sharing. Do not ever have 2 threads try to access the same data at the same time. And by sharing, I mean writing to it. Because what happens is that needs to get shipped from one CPU cache over to the other, and then back again, and it starts bouncing around, doing nothing of use, and slowing down your program. And that's why mutexes are slow. There's a new mutex in Linux called futex, but the basis is, it's still based upon we're both bouncing around trying to write to the same bit of memory to control access. There's an extremely useful data structure called ring buffers. It's a FIFO queue, first in, first out. It's a fairly simple data structure. But what's awesome about ring buffers is that they are easy to synchronize. They're very, very fast. And I'll get to that in a moment. So there's a lot of stuff we can talk about new synchronization, but these are sort of the 3 things I want to focus on. is avoidance sharing the rings, and another technique called RCU, read copy update, which I'll also talk about in a moment. So avoid data sharing. Here's one example of it. On my scanner, I was doing 25 million packets per second. There were 4 threads going on. Each thread was recording how many packets it was transmitting. Well, in every packet, it updated, plus, packet sent plus plus. Well, I can have a global variable and use an atomic operation, which is fairly slow, to try to add that. But then all 4 threads are sharing the same variable, and it's bouncing across the cache from one to the other, slowing things down. So what I do instead is each thread has their own private counter that only that one thread sees, pretty much. And it's never shared with the other threads. And then when it comes time to report on the command line how many packets per second I'm transmitting, a 5th thread comes along, sums them all up, and adds them together. It happens only once per second, so the fact that it gets sent around the caches doesn't matter. And then it's got great performance. So and that's what you do. And you saw that, by the way, in the change from Linux version 2.6. They had global counters. When you looked at an interface, how many packets were coming in, that was a global counter that was updated by all the different threads. And now they use this technique where each thread has their private thread local storage, updates the counters, and then they're collected by a separate thread. Here's what a ring buffer looks like. You allocate, let's say, 1,000 entries in the ring. So when you reach the end, you just go back to the beginning. So, in memory, yeah, it's linear, but conceptually, it's a ring. So you have one thread adding new data to the end of the ring, and it goes counterclockwise. And then you have another thread pulling data off the ring. There might be 2 separate steps of pulling the data off and then releasing it. That's why there's that separate thing there. So each thread is going around. If the producer is too fast, it'll fill up the ring. Or if the consumer is fast enough, it'll catch up with the producer and just be one step behind the producer. And there's a number of interesting things about this. One of which is that if you've got one producer and one consumer, you don't need to have any special synchronization steps, not even atomic operations. You can do it with just your normal read a variable or write a variable. And that's really cool. Another thing about it is that it avoids that data sharing problem again, because the producer and the consumer are on different parts of the ring. They're not writing the same variables, so they're not bouncing back and forth between the caches. So this is really, really fast. And this is the basis for underlying a lot of stuff that we have. For example, remember that I'm using the PF ring driver. It's called PF ring for doing the packet reception. That's because it's using a ring buffer. And in that case, the synchronization is between the network hardware and the user mode application. But if you're using a language like Erlang or other languages that pass messages between threads in order to achieve scalability, underneath there, they're using things like ring buffers. And it's such a useful data structure that it's worthwhile converting whatever it is that you have, even though it doesn't look like the best data structure, it's worthwhile converting your code so that you can leverage the awesomeness that is ring buffers. So here's what my scanner does, is the transmit threads are separate from the receive threads. That's sort of the asynchronous design. But when I grab a banner, I use TCP, I send a SYN, they send me back a SYN ACK, and the receive thread, I need to send an ACK back in the transmit thread. Well, how do I get that ACK being sent? Well, I just use a ring buffer between them. So that becomes the design. I have a pair of threads, a transmit and receive thread, that are paired together. And then, so I have 4 hyper-threaded cores. So that means 8 threads in the cores. So I have 4 transmit threads, 4 receive threads, and they're paired together, and each pair is connected via a ring buffer. So then I don't really have any synchronization issues. They're 4 essentially independent threads that see in their virtual world that they own the adapter, and it's hashing the incoming responses so it can link up properly with the transmits and receives. And it all works. So let's talk about the other technique I described, which was read, copy, update. And the DNS is a pretty good example of describing how read, copy, update works. So if you look in the Linux core these days, like Linux 3.6 code, you see RCU everywhere because Linux has just thrown that technique everywhere throughout the kernel because it scales really, really well with lots of cores, lots of CPU cores. So the way it works is consider that DNS, modern DNS has an operation called update, which is I've got www.example.com. I want to add a new record to that. Like I've got a new IP address that uses, or I want to change the IP address. Well, let's think about I've got a multi-core DNS server that's in the middle of all of this is processing incoming requests for www.example.com, spitting back the IP address while I'm trying to update it. So what I do is I don't disturb the other threads. I let all the existing threads go off without any synchronization using the existing read-only copy. As far as they're concerned, it's read-only. They can't change it. But the update thread, the one that's writing it, creates a copy of that record instead of changing it. It then does all its changes to the copies. And when it's done, it then just swaps the pointer. It says, and now points wherever that hash table is that points to the old entry, now points to the new one. And that doesn't need to be done as any special operation. It's just a pointer swap. As long as you don't cross cache line boundaries, you can write a value into memory, and then suddenly it changes. So it swaps it. Now the problem here is that as threads are all trying to read it, some threads will read the new pointer, some threads will read the old pointer. So when you look at the output of this DNS server, you might see in a strange order at that moment of swapping that out of order, you'll see some of the new ones and some of the old ones. And only at that point do you see maybe that little change. So there's old response, old response, old response, new response, old response, new. And what happens is it waits until all threads have been done with the old copy, and then it reclaims the old copy. And it doesn't really need any, again, normally it doesn't need any special synchronization, not even atomic operations. So here's the results I get from all this. Is mass scan is 10 times faster. So I had mass scan pretty much complete, and then someone created a release of this thing called ZMAP. And ZMAP, their paper, by the way, is awesome. The results they've gotten from it they're huge, and they're really, really cool. But their scanner is only 1.3 million packets per second, because they're going through the Linux kernel. So I had to okay, time for me to check in my changes to mass scan, which is 25 million packets per second. And it's 25 million because I'm avoiding the kernel. Otherwise, the scanners are fairly similar. They're using mutexes and stuff, which is bad. But otherwise, we're both like asynchronous scanners that spew out packets. Likewise with the DNS servers, my server is 100 times faster than bind, but bind is particularly slow. There's lots of servers that are 10 times faster than bind. So my server is 10 times faster than those servers. It's far from complete though. And that's one of the important things about this. So we all know Nmap is the most popular port scanner. Why is my scanner not a replacement for Nmap? Well, it's because it does a lot of things worse than Nmap. Nmap does a host at a time. It selects a host at random or whatever that's going to choose a scan, then it scans the entire host. Mine does a port at a time. I'm spewing packets. I really don't associate one port with the other on the same host. And that requires more work on the back end to correlate results. Also, mass scan can't do some useful things like really do a good job at OS identification. It can grab banners, it can do a lot of other useful stuff, but there's some things that this doesn't really do at all. My DNS server has no database. It's intended to act as a slave and to mirror an existing database, something like bind. And actually, if we go back to the 1980s when DNS was first designed, they actually anticipated something like this. The design of DNS is that you have sort of a master database of what that really holds the authoritative copy of all the data. And then you've got mirrors throughout the internet that mirror that data. And the mirrors just reflect. They have no functionality other than just to reflect what's in the master database. And that, again, it goes back to that data plane design, back to the telecommunications companies, is you have the control system, in this case the bind server, which is fairly slow, but feature-rich and does lots of cool stuff. Someone goes, like last week I went to GoDaddy, registered a new domain name, and that domain name was instantly then replicated throughout the internet, so people could get to that domain. And then what I did was, using whatever GoDaddy's logic was, I did the red line. I went to the master copy, created a new domain, the .com database. And then instantly, that was then sent to all the other .com servers throughout the internet. Sort of the ones that were fast but feature poor. Okay, so here are the conclusions. Is we have software that was built back in the 1990s which should not be exposed to the internet as it is today. Should not be exposed to the billion hostile devices that's attached to it. And what those textbooks should have in them, the changes in how to build a scalable web application, should be using these techniques I described. Better synchronization, better thread scalability, that sort of stuff. Direct access to the network card instead of going through the networks, going through the kernel. And it should be built hardened with the idea that I've got hostile enemies I'm all directly attached with. This is supposed to be the animated GIF again, but it's supposed to be bouncing around here. It's supposed to show what Apache is like. So that's the end of my talk. Any questions?
What were some of your references as far as when you were bypassing using the Linux kernel? Where did you get some of your ideas from in terms of how to design?
So the question is what are some references I used in how to bypass the Linux kernel? And what sources did I use? Well, I first did this 15 years ago, where I had to come up with it all on my own. I didn't have any sources to work with. Nowadays, an excellent source to look at is Intel's data plane driver kit, DPDK. It's actually dpdk.org, dataplanedriverkit.org. And where they have their own network driver, like pfring, but it's a different network driver, but it's the same concept, ship it to user mode. And they've got their own implementation of like the ring buffer and some other cool cheap synchronization for threads. And the code is there laying out the plan for you, so that if you just do what their code allows, you'll by default create a nice scalable system. I don't like it for a lot of reasons, but it's actually really, really good. So if I hadn't already done this all myself, I'd just be going to dpdk.org and just downloading it and just building stuff with it, because it's pretty good. Unfortunately, there's no textbooks. You'll never read a textbook that says, here's how you bypass the kernel. When you go to a college professor, it's almost like a religion. They'll teach you the wonders of the kernel and how you should just follow what they do. It's like Catholicism. And if you don't do that, you're like evil and immoral. You had a question?
Yes. Do you know any existing frameworks that implement IPv4 on this level? Because I see that you actually basically requires IPv4, for example, TCP point, which is hard.
Right, the TCP state machine is hard. So the question is are there any good like TCP/IP frameworks that fit into this sort of model? Like a user mode TCP stack that I can just plug in. There are some researchers who've built their own stuff. There's also a commercial company called something, 6Wingate, I think is their name. They have a user mode one for sale. It's proprietary, closed source. When you get a device that has something, a proprietary device you plug into your data center, it'll often be the 6Wingate stack that they're using in a user mode TCP/IP stack rather than a kernel mode stack. So it's a very good, I assume it's a very good stack. I haven't really looked at it. But other than that, I'm just sort of playing around with myself with the user mode TCP. If you look at my scanner and how I do banner checking and how I do TCPs, the TCP state machine, it's really, really evil and nasty. So it's not something I could build to actually build a web server from. But it's great for doing the back and forth TCP exchange of give me your banner. I'll send you a TCP request, you send me the response, and I'll parse it. But yeah, there really isn't a good user mode TCP stack. By the way, if you're a university researcher, that might be something you might want to build, because that would be really, really cool if I could take like Nginx and just replace a user mode stack that goes a lot faster than going through the kernel. Any more questions? Okay. It's 2:55, so I guess that's it.
So you managed to fix it?
Yes. I rebooted.
Ah.
I have a question for you. I missed part of I had a quote. I think there would be interesting stuff to do also on data transfer like iSCSI or with
It'd be great for iSCSI.
Yeah, would there be room for improvement regarding this? And yeah, iSCSI could be.
Yeah, iSCSI with PF Rain would rock.
Yeah.
You could do a lot of interesting stuff.
Because I have a colleague of mine, she's doing research on this, and okay. And I missed all the interesting part of it.
Oh, the first part was more high level. Vision.
So basically, those rings, this is already what is in Linux, right?
Well, Linux has rings and stuff. They're in the kernel, and you don't really, it's not data structure.